Welcome to an exploration of one of nature's most fascinating contradictions, the surfactant paradox. The paradox is this: the same surfactant molecule can either stabilize droplets, keeping them perfectly intact, or destabilize them, causing them to merge and break apart. How is this possible? Before we dive into the paradox, let's understand what surfactants actually are. Surfactants are special molecules that have two very different parts with opposite properties. One end, called the head, loves water and is hydrophilic. The other end, the tail, hates water and is hydrophobic. This dual nature is key to everything surfactants do. You encounter surfactants every day. Soap molecules are surfactants. So are the phospholipids that make up cell membranes in your body. Surfactants naturally arrange themselves at interfaces between water and oil. At the interface between water and oil, surfactant molecules line up with their heads in the water and tails in the oil. This arrangement lowers the interfacial tension. Interfacial tension, gamma, is the force per unit length at the interface. It's measured in millinewtons per meter. Without surfactants, the water-oil interfacial tension is about 50 millinewtons per meter. That's a relatively high energy barrier. With surfactants present, this can drop to just 1 to 10 millinewtons per meter. The surfactants dramatically reduce the energy cost of having an interface. Now let's see how surfactants stabilize droplets at low concentrations. When surfactants coat an oil droplet in water, they create a protective layer. The heads face outward into the water, the tails face inward into the oil. This arrangement stabilizes droplets through three powerful mechanisms working in harmony. First, the reduced interfacial tension means less energy is needed to maintain the droplet surface area. Second, charged surfactant heads create electrostatic repulsion between droplets, preventing them from merging. Third, the physical presence of surfactant molecules creates steric hindrance, a physical barrier preventing droplets from touching. The electrostatic repulsion energy scales as charge squared divided by distance. Even small charges create significant repulsion at nanometer scales. Everything changes when we reach a critical surfactant concentration called the CMC. At low concentrations, surfactants preferentially go to interfaces, where they reduce energy most effectively. Below the CMC, surfactants spread out, coating all available droplet surfaces. This is the stabilization regime. But above the critical Micelle concentration, something fascinating happens. Surfactants start forming Micelles, tiny spherical aggregates in the bulk solution. A micelle has hydrophobic tails pointing inward, creating an oily core, while hydrophilic heads face outward into the water. For sodium dodecyl sulfate, a common surfactant, the CMC is about 8 millimolar. This is roughly 2 grams per liter. For cetyl trimethylammonium bromide, another common surfactant, the CMC is lower, around 1 millimolar. Now here's where the paradox emerges. At high concentrations, surfactants can actually destabilize droplets. This seems counterintuitive. If surfactants stabilize droplets, shouldn't more surfactant mean more stability? The answer reveals deep physics. The answer lies in two competing effects: osmotic pressure and solubilization. At very high concentrations, micelles can penetrate into the droplet core, swelling it from within and creating osmotic pressure. The osmotic pressure follows the Van 't Hoff equation. Pi equals nRT, where N is the molar concentration of solute particles. At 0.1 molar concentration, the osmotic pressure is about 250 kilopascals. That's more than twice atmospheric pressure, enough to burst droplets. Another destabilization mechanism is the Marangoni effect, caused by surface tension gradients. If surfactant concentration varies across a droplet surface, you get regions of different surface tension. This creates flows along the interface. The Marangoni velocity is proportional to the surface tension gradient divided by viscosity. Even small gradients create significant flows. These Marangoni flows can be strong enough to deform and even tear droplets apart, especially when surfactant is added rapidly. At extremely high surfactant concentrations, we see solubilization, where the distinction between droplet and micelle blurs. Large droplets break down into smaller and smaller particles, as micelles extract oil molecules from the droplet cores. The droplet radius equals 3 times the oil volume divided by the total interfacial area. As surfactant increases area, radius decreases. Eventually, you reach a state called a microemulsion, where droplets are so small, typically 10 to 100 nanometers, that they're thermodynamically stable. Microemulsion droplets are in the range of 10 to 100 nanometers, much smaller than typical emulsion droplets at 1 to 10 micrometers. We can map out this behavior on a phase diagram showing stability versus surfactant concentration. The phase diagram shows three regions. At low concentration, droplets are stable. At intermediate concentration, there's a transition zone. At high concentration, we see destabilization. The critical transition typically occurs near the critical micelle concentration, though the exact point depends on many factors. Let's work through a concrete numerical example to see these effects quantitatively. Imagine we have oil droplets with a radius of 1 micrometer suspended in water. That's 1 micrometer, or 10 to the minus 6 meters. The surface area of one droplet is 4 pi r squared, which equals 1.26 times 10 to the minus 11 square meters. Without surfactant, the surface energy is gamma times area, or about 6.3 times 10 to the minus 13 joules per droplet. Now let's add surfactant at 1 millimolar concentration, just above the CMC for many surfactants. The interfacial tension drops to about 5 millinewtons per meter, a tenfold reduction. The new surface energy is now 6.3 times 10 to the minus 14 joules, 10 times lower. This stabilizes the droplets. However, if we increase concentration to 100 millimolar, osmotic pressure starts to dominate. The osmotic pressure is now 248 kilopascals, creating enormous internal stress. Compare this to the Laplace pressure, which is only 10 kilopascals for our droplet. The osmotic pressure is 25 times larger. The result is that droplets swell under this osmotic pressure and eventually burst or dissolve completely. This paradox has profound implications for many real-world applications. Drug delivery, food emulsions, cosmetics, paints, detergents, and oil recovery all rely on controlling surfactant behavior. In drug delivery, we need stable nanoparticles that won't aggregate before reaching their target. In detergents, we actually want destabilization to solubilize and remove dirt and oil stains. In food science, products like mayonnaise and milk must remain stable for months without separating. The key to harnessing surfactants is understanding how to control this delicate balance. So how do we maintain stability when we need it? There are several strategies. One approach is to mix surfactants with different properties, combining ionic and non-ionic surfactants. The hydrophilic lipophilic balance, or HLB, quantifies this. Values from 3 to 6 favor water and oil emulsions, while 8 to 18 favor oil and water. Another strategy is using polymeric surfactants, which provide enhanced steric stabilization through their large molecular size. We can also control temperature and pH to tune electrostatic interactions and surfactant solubility. Polymeric surfactants create thick protective layers around droplets, providing mechanical barriers to coalescence. Let's take a deeper thermodynamic view of why this paradox exists. The Gibbs free energy change equals enthalpy change minus temperature times entropy change. At low surfactant concentration, the enthalpy change from reducing interfacial energy drives surfactant adsorption to interfaces. This enthalpy change is negative because we're lowering interfacial tension and energy, making the process spontaneous. At high concentration, entropy favors Micelle formation because it releases water molecules that were structured around surfactant tails. The entropy gain from releasing these ordered water molecules is substantial and positive. The free energy of Micellization combines the enthalpy of bringing tails together with the entropy gain from water release. Above the CMC, Micelles in solution compete with droplet interfaces for surfactant molecules, destabilizing the droplets. The surfactant paradox is also deeply connected to dynamic processes and timescales. Surfactant molecules don't instantly coat surfaces. They must diffuse from bulk solution and then adsorb to interfaces. The diffusion timescales as distance squared divided by diffusion coefficient. For typical surfactants, the diffusion coefficient is about 10 to the minus 10 square meters per second. For a droplet 1 micrometer away from a surfactant source, the diffusion time is about 10 milliseconds. If droplets collide before they're fully coated with surfactant, they can coalesce because the protective layer isn't complete. When two droplets approach each other, if the surfactant layer is incomplete, they can bridge and merge at the contact point. This is why adding surfactant too slowly can fail to stabilize an emulsion. The droplets collide and merge before protection is established. Now we can fully understand and resolve the surfactant paradox. At low concentration, below the CMC, stabilization mechanisms dominate through reduced surface tension and electrostatic repulsion. At medium concentration, near the CMC, we achieve optimal stability with complete surface coverage but minimal bulk micelles. At high concentration, above the CMC, destabilization mechanisms emerge through osmotic pressure, solubilization, and Micelle competition. The key is finding that sweet spot at medium concentration where stability is maximized. Too little or too much both cause problems. The surfactant paradox teaches us that molecular behavior emerges from competing forces operating at different length scales and concentrations. Understanding these principles enables rational design of emulsions, from pharmaceuticals to foods to industrial processes. Nature exploits this very paradox in biological membranes, where phospholipids dynamically assemble and disassemble to control cell processes.